Hello, everyone. Welcome to SecChooseCon 2026. I am Arun, Cloud Platform Engineer, and my expertise primarily focused on cloud infrastructure management, DevOps, SRE, platform engineering, cloud security. And I'm going to talk about how we can leverage observability-driven reliability practices for building and securing AI agent infrastructure. Yeah. To start with an introduction, so when we talk about AI agents today, it is important to stop thinking about them as a simple LLM endpoints. So they are autonomous, distributed execution systems. So they do much more than generate text. So they plan, retrieve context, invoke tools, call APIs, and in many cases, they take actions across many environments. So that means we are no longer operating a single inference service. So we are operating an end-to-end decision and execution pipeline. So and that changes the infrastructure problem as well. So the challenge is no longer limited to model or LLM quality or response accuracy. And now we also have to consider orchestration reliability, tool and API failures for agents, or unsafe or unintended actions of the agents, data exposure risks, policy violations, even like cost increase. So, in other words, the operational surface area broadens significantly, and the consequences of failure become much more severe now. So, this is why traditional application monitoring is no longer sufficient as of now. So, in conventional systems, we often focus on uptime or infrastructure health and service latency. But in agent systems, failures can be broader. An agent can be available, and but still it can be wrong. It can respond quickly and still violate a policy. Can complete a task and still create a safety or security governance issue. So the failure domain expands from availability into correctness, safety, security, and control. So this is where the observability becomes much more than a monitoring function solution for conventional infrastructure. So and it becomes the control plane. So to operate these AI agents securely, we need correlated observability across the full execution life cycle of the AI agents. So by correlating traces, metrics, logs, security events, and evaluation signals, we can achieve real-time visibility across the full agent lifecycle. So that gives us the ability to measure reliability, detect abnormal behavior, or enforce security boundaries and operate AI agents in a way that is both trustworthy and resilient. This is the AI agent's operating loop. So before going deeper, let's align on that operating loop. Like an AI agent usually starts with the user intent or any system trigger, then interprets that intent, it creates a plan, retrieves the context it needs, and it invokes an LLM model, calls tools, and evaluates the outputs, and may update the memory or take any action based upon the input. So the important point is that this loop is dynamic and it can change. The path can change based on the retrieved context, model output, policy decisions, or tool responses. So that means the reliability boundary is not a single service endpoint. It is the complete run of the agent. So when we talk about observability in the next slides, we are not only observing the infrastructure, we are observing the agent's reasoning path, the source of context, the permissions it used, the decisions it made, and even the side effects it produced. Next, we'll focus on like why AI agents change the reliability and threat model. So, so the AI agents change the reliability model because they are not just returning generated text. They make decisions across a chain of components like orchestration logic, prompts, memory, retrieval systems, model calls, tools, APIs, and even policy checks. So in a traditional service, we usually ask whether the system is available and check whether and do some health checks, whether the system is performing well or not, and whether the latency is acceptable or even the error rate is within the limits. So with AI agents, that is not sufficient. Okay, the platform can be healthy from an infrastructure perspective, but while the agents produce an incorrect answer, it may like select the wrong tool, and it may leak some information or perform an unauthorized or undesired actions. Um, this also changes the threat model. So the agent's autonomy increases the blast radius of prompt injection, retrieval poisoning, excessive permissions, and compromised tools. So a malicious or malformed instruction may not only influence the response, it may influence an action. So that means every agent step must be observable, and every privilege action must be governed. So the key reliability question becomes: so can we prove what happened, why it happened, which controls were applied, and whether the outcome stayed within the defined reliability and security boundaries? So AI agents turn reliability into a combined problem of distributed systems engineering, security governance, and behavioral evaluation. So in this slide, we focus on the observability telemetry strategy. Um, it highlights like a core principle for operating AI agents in production environments. So every agent has to run to be queried end to end. So the data or even the how we need to track how the agents works from end to end. So the goal is not just collect telemetry data for dashboards. It is to build a runtime evidence model that lets us reconstruct exactly what happened during a single agent execution. So we want to see who initiated the run, which agent, prompt, and model versions were involved, what tools were called, or what policies were triggered, and how the run agent performed, and whether it stayed within the security and reliability boundaries. So on the left side, we can see the observability telemetry layers that enables this approach. So the metrics provide the key operational signals such as latency, errors, token usage and cost, logs and events, capture prompt metadata, tool arguments, policy decisions, and evaluation outcomes. And the traces show the full execution path across workflow, agent, model, retrieval, and tools. So evaluations add quality signals like correctness, safety, and like task pass rate. And at last, the security signals add identity, access, anomaly, and DLP context. On the right side is the correlation, the agent correlation envelope. It shows the minimum set of IDs and dimensions needed to join all the data. That includes the trace and span IDs, agent run ID, tenant and actor context, versioning fields such as prompt, hash, and model version, and governance fields such as policy decision ID, risk score, and SLA window. So once the correlation is in place, like every agent run becomes reconstructible, explainable, and even it can governed. So this is what turns raw telemetry data into observability-driven reliability. So under the threat and reliability model, we focus on like what needs to be observed from the agent perspective. So one agent runs or queryable, like when we are able to track the activities of the agent, we need to be explicit about like what must be observed. The first category is prompt or context manipulation, where direct or indirect prompts alter goals, tool arguments, or policy interpretation. So the second is the memory or retrieval poisoning, in which untrusted content alters future behavior or contaminates RAG grounding or retrieval augmented generation grounding. And cost and availability failures manifest as token spikes, recursive loops, retries, queue saturation, or even model denial of service patterns. And the other one, like tool misuse and excessive agency occur when an agent involves risky actions, expands scope, or changes tools beyond the intended purposes. And the other one, like inference degradation, includes latency, provider errors, model uh, swaps, or like drift, hallucination, or even the invalid schema output. And at last, the identity and supply chain drift that include like overprivileged tools, stale secrets, unverified package or model provenance, and misconfiguration frameworks. For each category, so we should define the telemetry signal or data, the expected baseline, and the control action when this signal crosses a risk threshold. So in this slide, we can focus on the trace anatomy of an agent run. This shows what an agent trace should contain. So that trace should begin at a request authentication, move through intent classification and policy pre-check, then capture that agent plan and rejected tool candidates or like retrieval query, ACL filtering, model inference, token usage, and much more. So this is not just for debugging. The same trace data support forensics by showing who triggered that agent or who triggered the agent run, which model and prompt version were used, which tools were executed or used, and what changed. So it supports performance debugging by showing where latency, cost, drift, or semantic failure appear. So it provides policy evidence by recording which guardrail, approval, or authorization decision allowed the action. It also supports security direction by surfacing anomalous tool sequences, retrieval sources, or output patterns. So this is a reference architecture. um, it shows how we can fit all the pieces together. So users and applications enter through a zero trust ingress layer that handles the authentication, authorization, DLP, and rate limits. Um, and the agent runtime or orchestrator coordinates the planning, execution, and memory. From there, the requests flow through the LLM gateway for routing and evaluation hooks. So through RAG and memory with ACLs, provenance, and trust labels, and through the tool or MCP gateway with schema, scopes, and approvals. So the policy decision point sits in the control plane and evaluates identity, attributes, behavior, and safety policies before sensitive actions can take place. So on the telemetry side, the open telemetry collectors capture metrics, logs, traces, and events. And the run ledger store. Yeah, so the run ledger and the evaluation store preserves the trace aligned evidence. So and the SLO engines, SIEM, SOR systems use that can that are used for the burn rate analysis and detections. And at last, the remediation, the closes the loop with the rollback, quarantine, read only mode, and or other or remediation actions. So the architecture separates the planes like execution, control, tools, telemetry, and remediation planes, but keeps them connected through the correlation IDs and the policy decisions. So this slide shows the what are all the SLOs that we can define for AI agents. So for agents, SLOs need to extend beyond the uptime. So availability is not simply whether the service is responded. It is whether the eligible agent ran successfully or not. So latency should measure end-to-end task time with different expectations for simple and multi-step workflows. And the next one, the cost. So it needs its own SLI, such as the 95th percentile cost per successful run, because the token burn and repeated calls can become a production instance. And the other one is the correctness. This can be measured through the task evaluation pass rate, and then the groundedness measure whether the checked claims are so supported. And the other one is the safety can be tracked as one minus the unsafe output or unsafe action rate. And the tool conformance assesses whether the tool's calls were valid, policy checked, and authorized. So each SLO needs an action attached to it, and the goal is to make the SLOs actionable. And this is the operational life cycle. So it combines the security evaluation and the SRE practices. So the operational lifecycle shows how security evaluation and SRE practices should be integrated rather than just treated as separated workflows or work streams. So in design, we define the threat model, SLOs, tool scopes, and data classification. In the build phase, like we instrument the guardrails, policy hooks, and audit schemas. And under evaluation, we run tests, trajectory evaluations, and even we perform the load or cost tests. So in the deployment, we can use canaries, feature flags, and versioning of LLMs and prompts and rollback plans. And in the run phase, we can monitor the SLO alerts, perform the anomaly detection, or enforce the anomaly detection, and also implement a budget awareness. So in the learning phase, we feed the data for incidents into postmortems, data set refreshes, policy updates, and evaluation drift reviews. So the gates at the bottom are the control points. So there is release gates before production, runtime gates during execution, and the learning gates after incidents. So this is how agent operations become continuously governed. So in this slide, we'll focus on the how the detection occurs. How we can detect using observability, and we just need to focus on the alert on behavior, not just errors. So detection should focus on behavior. In agent systems, a successful request can still be unsafe, or it can be incorrect. So we need the alerts that reflect meaningful changes in behavior. Here, two velocity spike indicate a loop or unexpected automation, and the privilege drift may show that tool scopes or credentials have expanded beyond what was approved. The retrieval anomalies can expose poisoning, unauthorized context, or unusual use of sources. And the memory mutation spike may signal unintended persistence or contamination. Token burn rate anomalies indicate cost and availability risks. Policy block surges can reveal attempted misuse or bad releases or prompt injections. And the evaluation drift tells us the agent's production behavior that is like drifting away from the tested or the baseline expectations. The value comes from the correlation. So these signals should be joined to run IDs, actors, policies, tools, prompts, and model versions. So the alert explains the behavior rather than just simply reporting as a noise or just an alert. So how the automated remediation works? How we can reduce the autonomy when the risk increases? So automated remediation should reduce autonomy whenever the risk increases. The response does not have to jump immediately from normal operation to shutting everything down whenever a risk occurred. So the first step is to observe. we can increase the sampling and capture redirected evidence. Next, they constrain the workflow by lowering the max steps, capping tokens, and forcing citations. If risk continues, supervise by requiring approval or human in the loop review. Then isolate the affected tool or memory store or MCP server to contain the blast radius. So if the issue is tied to a release, uh, roll back the prompt, model, tool, registry, or policy. Finally, the kill switch disables the agent workflow while preserving the forensics ledger. So the important principle is that the remediation should be policy driven and reversible wherever is possible. We want the system to degrade safely, maintain evidence, and preserve trust while while operators can investigate. So this is the implementation roadmap. So this roadmap turns um, the framework into an implementation sequence. So in the first, maybe like in the 30 days, like can focus on instrumentation, where we can define the agent run IDs and trace taxonomy, um, capture model, tool, RAG, and guardrails, redact and classify prompt and tool payloads, and start dashboards for latency to track the latency cost and tool errors. And after like 30 days, we can focus on the SLOs and controls, publish latency, cost, correctness, and safety SLOs, add budget burn alerts and sampled evaluations, and require approval for high impact actions, like requiring human approval to initiate any high risk actions. And after 60 days, like we can begin automation to enforce policy based on budget, burn on risk score, add anomaly detection and SIEM correlation, automate and containment and rollback playbooks. And we can also create feedback loops from postmortems back into the evaluation data sets. So the intent is to move deliberately from visibility to enforcement without skipping the evidence layer. Yeah. So to close it up, the central message is that secure AI agent infrastructure requires observability, reliability, and governance to work together. So agent systems create value because they can plan, retrieve, and act. But those uh, capabilities can create operational risks. So we cannot manage those risks with just uptime dashboards or alerts. We need to trace the agent runs. We need the correlated security and evaluation signals, actionable SLOs, behavior-based detection, and even remediate to reduce the autonomy whenever the risk occurs. So when those practices are built into the architecture, observability becomes more than just monitoring. It can become a safety and control system for AI agents. Thank you.